Hello, my name is Jinwoo, and I would like to present Booster Shot, boosting stacked tomography transformations for multi-view pedestrian detection with attention. First, I would like to define the problem, which is multi-view pedestrian detection. In this case, we use multiple cameras, as seen in this image, to detect pedestrians. And eventually, we create a bird's eye view heat map. In this case, we use overlapping camera views, and the cameras have fixed world coordinates. For example, they might be static CCTVs. In this kind of problem, multi-view aggregation takes a very important role in collecting information across views. Let me first introduce previous methods to approach this problem. On the left side, we have the first method, MVDET, multi-view detection with feature perspective transformation. In this case, we take the input images, put them through a feature extractor, and with an additional training loss and chord-conv methods, using homographies to transform this to the ground plane, we pass this through a final CNN to get a bird's eye view heat map showing where people are. Another study is stacked homography transformations for multi-view pedestrian detection. Here, the authors suggested using multiple homographies instead of simply the ground plane. Using these, along with a soft selection module, which basically assigns the best possible homography plane for each pixel in the image, the authors provided state-of-the-art performance over MVDET. Finally, we have multi-view detection with a shadow transformer, MVDET-R. In this case, the authors attempted to apply a shadow transformer, a type of deformable transformer, to the latter part of the network, and they also introduced various view-coherent affine transformation augmentations in the earlier stages in order to introduce augmentation to this type of problem. Let me show you an overview of our approach. First off, we start off in the same way with multi-view images. We then put these through a feature extractor. We then put them through our proposed Homography Attention Module, HAM. We then get projected features and put them through a final bird's eye view heat map generator, a type of CNN or transformer, to get a heat map, which we then post-process in the same way as our previous works, using thresholding and non-max suppression. I will further explain our Homography Attention Module in the next slides. First, I would like to introduce our channel gate. In the channel gate, depending on the homography, different channels have different levels of importance. The first part of our channel gate is our channel selection module. This part outputs distinct tensors for each homography. It's basically a type of attention value, which we then use in the top K selection module that comes afterward. Here, we choose the K max values from these input channels and output them directly. So we're basically selecting the top 2, in this case, out of 8 channels. You can see here that in the second and third ones, you have the same 7th channel being used twice, and that is entirely possible. Then I would like to move on to our spatial gate. In the spatial gate, for each view and homography combination, different spatial features have different importance. And we reflect that by using this method, where we take the pooling, concatenate, put them through a CNN to get attention values that differ for each pixel. And this kind of network is individually applied to each of the homographies, so it is specific to each view and homography combination. So I'd like to move on to showing you our performance comparison with previous methods. So I highlighted in blue the results of our method, Homography Attention Module, applied to previous methods, such as MVDET, SHOT, and MVDET-R. You can see that overall, we achieved state-of-the-art performance. And also, I'd like to introduce Booster Shot. So Booster Shot is basically applying everything that our previous works did, such as the augmentations, along with our Homography Attention Module, to provide an end-to-end state-of-the-art performance method to multi-view pedestrian detection. You can see here that Booster Shot, which is using the CNN, traditional CNN in the lattice part of the network, and Booster Shot plus Transformer using the deformable transformer type architecture, both show the best performance overall. Next, I would like to move on to showing you some visual representations of our attention. So first off, we have the homography-wise output from the channel selection. You can see here that for each of the homographies, the part of the person highlighted differs, and it makes sense to go higher up as the homographies go farther and farther away from the ground plane. In the second one, we can see camera view-wise output from our channel selection module. And you can see how in each camera view, the channel selection module attends to a similar region of the person. Next, I would like to show you the results from comparing our ham with existing attention mechanisms, such as squeeze and excitation, CBAM, and CCG. So all of these previous methods show slight improvement over the no attention case, but they cannot replace our homography attention module in terms of performance, as it shows significant improvement over the three. I'd like to introduce some further ablations regarding computational complexity and performance. So as I said before, we are taking the top K channels in our channel gate second part. So you can tune this actually to fit your computational complexity and performance needs. On the right side, you can see that for our 5 homography default case, top 16 has the best performance. And on the left side, you can see how the computational complexity differs depending on the top K value. And on the bottom, you can see that actually booster shot is not computationally costly and is also quite a fast runtime. Next, I would like to move on to our experiment showing performance under spontaneous camera failure. In this experiment, we're simulating real-world scenarios where cameras can often fail. So we have a failure rate, which is the ratio of frames for which at least one camera fails. The number of cameras failing at each point in time is entirely random. So if the frame is failing, then we can have anywhere from 1 to n, which is the total number of cameras, fail. So worst case, every single camera could be failing. And for camera failure, we replace the image with all black RGB 000 pixels to simulate no feed coming through. So here you can see that as the failure rate increases, performance degrades. However, I would like to point out that the difference is not that large. And also for a realistic estimate case, which is roughly 2%, 0.02, there's actually no degradation in most of the metrics, close to no degradation. And this shows that our method is reasonably robust in real-world situations. So thank you for listening. Our poster session is on day 1, and you can contact me through the following email. Thank you for listening.